Hi everyone, welcome back to Derive It, and we're going to be solving valid anagram today. So we're given two strings S and T, and we want to see if they're anagrams of each other, which just means we can rearrange the strings into each other. So the thing to notice about this problem is that if we're given this as a string, then we can rearrange this string into any string with one K, one N, and two E's. So the count of each letter has all the information we want to figure out if two strings are anagrams of each other. They're anagrams whenever the counts are equal. So for example, something like keen and knee would be anagrams because they both have the same counts of each letter. So the way we can solve this problem is we can just build a hash map of the count of each letter. So in order to look up the number of K's we have, we can just put K along this edge, and we can put the count along this edge, and we can build the hash map by just starting here, and then we would see an N. So we would say, okay, we have one N, and then an E, and we just keep building the hash map like this. One E, we follow this arrow, and now we make it two E's. And so this would be the hash map of the count of each letter. And so that's how we're going to solve this problem. So we're just going to create a hash map for the first string S, and one for the second string T, and then we're going to compare them to make sure the two counts of every letter are equal to each other. So we can just create the first hash map, count of letter S, and the second hash map, count of letter T, and now we just want to build them. So we want to iterate through every letter of S. So for every letter in S, we just want to increase the count that we've seen so far. And at the end of this for loop, we'll have the hash map, the full hash map. So you would think that this would work, but actually we start with an empty hash map. So when we say count of letter S of letter, letter is not going to be in the hash map. We want to actually default this hash map to 0 if the letter isn't already in the hash map. So I'm just going to do that by saying 0 if letter not in the hash map. Otherwise we can just use this as we wanted to. So this builds the hash map for S, and we can copy and paste this code to build the hash map for T. And then we just want to compare the two hash maps to make sure they're equal. So let's make sure this runs. Alright, so I ran it a couple of times to see how good we could get it, and it beats a lot of people, but the memory is still pretty bad, and there's an optimization you can use to get this memory even lower. It just involves using one hash map instead of two hash maps, so all it does is halve our memory, but it's not very interesting. It's kind of just a trick, so I'm just going to put that in the videos right up. The link will be in the description. So the time complexity of this, we're iterating through every letter in S, and we're doing, this just takes one operation, so that's O of N, and we're iterating through every letter in T, and that takes M. So it's O of N plus M. That's the length of S and T. And then the equals, how much time does that take? So each of these hash maps only has one entry for each letter, A through Z. So when we do this comparison, it's just O of 26, which is the same as O of 1. So the time is just killed by the O of N plus M time. And so what's the space now? Well, we only store up to letters A through Z in either of these hash maps, so that's just O of 26, which is really O of 1. It's constant space. And what this means is that if the problem were huge, we wouldn't need to use any more space than we do now. O of 1 means that. Alright, so I hope that was helpful, and hope to see you guys next time. Thanks.